Hello, thanks for stopping by my poster. My name is Hongrui, currently a postdoc at MIT. Here we present, for the first time, fine structure of the Garlock fault zone resolved from Ridgecrest aftershock data recorded by dense linear arrays. The left lateral strike-slip Garlock fault runs northeast-southwest along north margins of the Mojave Desert of Southern California. Although no significant ruptures have occurred in the past century, the Garlock fault is capable of producing major earthquakes, as indicated by paleoseismic evidence. However, basic aspects of the seismological structure of the Garlock fault have not been imaged so far. Data recorded by two dense linear arrays, B4 and A5, are used to infer internal structure of the Garlock fault zone. Both arrays are deployed after the 2019 Ridgecrest sequence and recorded continuously in the field for about 1 month. The station spacing is 100 meters, and the array aperture is 8 km for array B4 and 2 km for array A5. Direct P and S waves and fault zone phases are analyzed to provide a comprehensive view of the internal fault zone structure. For teleseismic P waves, 3 teleseismic earthquakes recorded by the array A5 are analyzed. After proper correction, we find that, in general, the P wave travels faster in the crustal block north of the Garlock fault than that propagating inside the southern block, suggesting a contrast in P wave velocity across the Garlock fault. For P waves from local events, we use hypocenter distance to correct for the wave propagation effect, and then extract P wave arrival time pattern that is associated with velocity structure beneath the array A5. Results for an example event indicated in the top right figure is demonstrated here. Similar to teleseismic data, P waves from local events also show a velocity contrast across the Garlock fault, with the north side having a higher velocity. In addition, a about 500 meter wide low velocity zone that further delays the P wave is identified. This velocity contrast across the Garlock fault also produces head waves. One example of such candidate is shown here. The event location is indicated in the top right. The red and blue curves denote the peak and onset of the direct P waves, whereas the green curve denotes the fault zone head wave arrivals, which is only seen in stations on the top of the slower crustal block, south of the Garlock fault. The separation time between the head wave and P wave suggests the velocity contrast across the Garlock fault is at least 5%. In addition to P waves, we also identify a damage zone that significantly amplifies S waves. In this figure, we show the S waveforms recorded at the vertical component from an example event, and quantify the amplification factor as the multiplication of peak ground velocity and root mean square value. The amplification factor stands out clearly for a about 300 meter wide zone south of the Garlock fault, marked by the blue bar, and likely outlines the fault damage zone, which overlaps nicely with the low velocity zone identified from P wave arrival time before. This amplification pattern is consistently seen from many events, as the red curve in panel C depicts the amplification pattern averaged over many candidate events. In recordings of array B4, we observe strong and coherent secondary arrivals between the P and S arrivals that are likely P waves being reflected from the Garlock fault interface. One example is shown in this figure for an event in the colored circle. P and S arrivals are depicted by the dashed curves, while the reflected arrivals are over here. We calculate the theoretical travel time for the reflected waves using a constant velocity model and the ray paths shown in panel A. The predicted arrival time for the reflected waves is illustrated as the blue curve, agree very well with the observed arrival times. This again is consistent with the observation of a strong velocity contrast across the Garlock fault. To further constrain the geometry of the Garlock fault, we use diffraction migration to image the reflection interface using all the candidate events with clear reflections. The image obtained using a 1D velocity model for the migration is shown on the right in map view at depths of 4 km. And a depth cross-section at the blue dashed line is shown on the left. In general, the image has bright colors beneath the surface trace of the Garlock fault with a near vertical dipping angle. So in summary, the resulting fault zone image reveals a strong velocity contrast across the near vertical dipping Garlock fault that generates clear fault zone head and reflected waves. Besides, south of the surface trace of the Garlock fault, a low velocity zone with a width of about 500 meters that further delays P wave arrivals, and a about 300 meter wide damage zone that significantly amplifies S waves are identified. Modeling of fault zone trapped waves and migration of reflected waves using 3D velocity model will be included in the future. Thank you.